Hello students, welcome to Unoya. My name is Rizwan. I hope you all are doing well. So in this video, we'll be discussing about the remaining topics of real numbers. Okay, we have discussed the introduction, the starting part of the real numbers in our last video. Okay, I'll provide the link for that video in the description. Okay, so in this video, we'll discuss the remaining portions. Okay, so let's move into our discussion. So last in the last video, we stopped our discussion here. We discussed about fundamental theorem of arithmetic, and we discussed about the prime factorization of numbers. And we also solved a question regarding finding the LCM and HCF of two numbers using prime factorization. Okay, now in this video, I would like to start with this question number 5, because all other questions are similar with the questions that we have discussed in the last video. Okay, so here I will start with this question, the fifth one. You can read, check whether 6 raised to n can end with digit 0 for any natural number n. That is the question. Okay, we have an expression 6 raised to n. And the question is, can this 6 raised to n end with a digit 0? End with the digit 0 for any natural number n? That is the question. Okay, so let's solve this. Okay, so we have to begin with this one, 6 raised to n. Okay, this is our topic of discussion. Okay, and we have to check whether that is it possible to end this n for this 6 raised to n with 0, or can the unit digit of this number, the digit in the unit place of this number, be 0? That is the question. For that, we will use the prime factorization. Okay, we can write 6 as 2 into 3, right? This you will get if you prime factorize 6. Okay, 6 equal to 2 multiplied by 3. Okay, if you take the exponent n on both sides using the properties of exponents, 6 raised to n becomes 2 multiplied by 3 whole raised to n. Okay, that means taking the exponent n, taking the power n on both sides, which means we can write 6 raised to n equal to 2 into 3 whole raised to n. This can be written as 2 raised to n multiplied by 3 raised to n, right? Using the properties of exponents. A into b whole raised to c equal to a raised to c multiplied by b raised to c, that property. Okay, so this is actually the prime factorized form of 6 raised to n. If you prime factorize 6 raised to n, you will get 2 raised to n multiplied by 3 raised to n for any natural number n. Now come to our question. According to our question, we have to check whether this 6 raised to n can end with 0. That is the question. Now, we know that for any number, if that number is ending with 0, that will definitely be divisible by 5, right? If a number is ending with 0, if you can see 0 at its units place, then definitely that number is divisible by 5. For example, 10 is divisible by 5, 20 is divisible by 5, 50 is divisible by 5, 150, it is also divisible by 5, and then 260, 1150, 1230, all such numbers. If a number is ending with 0, then definitely that is divisible by 5. Okay, so we will use that property here. Here, if this number 6 raised to n, if it is divisible by, if it is ending with 0, then it should be divisible by 5. If it is divisible by 5, then we have to find 5 in its prime factorized form, right? If a number is divisible by 5, then definitely we will find 5 in its prime factorized form. But look here, this is the prime factorized form here. 2 raised to n multiplied by 3 raised to n. This is the prime factorized form. Can you see 5 here? No, only 2 and 3. You cannot find 5 in the prime factorized form of 6 raised to n. We have only 2 and 3. which means this 6 raised to n is not divisible by 5. Okay, this 6 raised to n is not divisible by 5. That means we cannot have this number ending with 0. Okay, so that is the answer. Okay, we cannot find, or we cannot find, yes, we cannot find 0 at the unit place of 6 raised to n. Okay, hope that is clear for you. Let's move to the next topic. Yes, revisiting irrational numbers. Regarding irrational numbers, we have studied it in the class 9th. Okay, and I have given some introduction regarding these numbers in the last video also. Okay, you can find it in the description if you didn't see that. Okay, now regarding irrational numbers, we can divide the entire real numbers into two parts. Okay, we can divide the entire real numbers into two parts. Okay, first one is rational numbers and second one is irrational numbers. Rational numbers are those numbers that can be represented in p by q form, one integer by another integer. So irrational numbers are those numbers that cannot be represented in p by q form. Okay, such numbers are known as irrational numbers. Okay, we have studied it already. For example, root 2, root 3, root 15, pi, minus root 2 by root 3. All these are irrational numbers. We cannot represent these numbers in p by q form. Okay, these things we have discussed in the earlier classes. But still we didn't prove that root 2, root 3, or root 5, such numbers are irrational. How can we prove that? In this video or in this chapter, we will study these things. Okay, we are studying these things in this chapter. We will prove these numbers, root 2, root 3, root 5, okay, 1 by root 2. Such numbers are irrational. We will prove this. Okay, so in the remaining part of this video, I'll be discussing this. For that, this theorem is necessary. Without this theorem, we cannot prove. You can read this, theorem 1.2. Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. That means, suppose you have a prime number P, and you have a positive integer A. Okay, if P divides A square, that means A square is divisible by P. Okay, A square means square of A. Okay, if that A square is divisible by P, or P divides A square, then definitely this P divides A. Okay, I'm repeating. Suppose we have a prime number P. We can have many prime numbers like 2, 3, 5, 7, okay, 11. All these are prime numbers. Okay, so P can take any of such values, and A is any positive integer like 1, 2, 3, 4, 5, 6, 7, etc. I can take any of these values. If you have these two numbers, one prime number P and a positive integer A, and if P is dividing A square, or if A square is divisible by P, the square of that positive integer A, that is A square. If that A square is divisible by P, or if P is dividing that A square, then definitely that P divides A. If P is dividing A square, then that P will divide A also. Okay, this is an important theorem. We will use this theorem to prove the irrationality of some numbers. Okay, the proof of this theorem you can see here, but that is not important in your exam point of view, so I'm not discussing here. Okay, you can go through that. Okay, next after that you can see theorem 1.3, root 2 is irrational. Okay, you can see the proof below. It's a solved one. Okay, below that you can see the entire proof. After that you can see in the example 5, prove that root 3 is irrational. For that also you can see the proof below. Okay, you can see the solution below. Okay, and you can also find some similar question like show that 5 minus root 3 is irrational, and 3 root 2 is irrational. Okay, for all these questions you can see the solution also below that. You can read that. But here you can see the exercise 1.2. Okay, for these questions you cannot find the solution in the textbook, so I am solving these questions. Okay, question number 1, 2, and one of the sub questions in question number 3. If you can understand all these questions, if you listen carefully to my explanation of these questions, then you can easily understand all these things. Okay, so I'm not doing these questions here in this video. I will be doing only this one, exercise 1.2, question number 1, 2, and one of the sub questions of question number 3. If you are thorough with these, then you can easily go through all these things. Okay, you will find this easier. Okay, because all are in the same form. Only the difference is with the numbers only. Okay, all the methods are same. Okay, So let's begin with the first one. Prove that root 5 is irrational. This one I will prove here. And above this, we have seen regarding proving root 2 is irrational and root 3 is irrational. Okay. All methods are exactly same. Okay. All are same. The only difference is that in the case of root 2 and root 3, you will find 2 and 3. Here you will find 5. That is the only difference. Okay. All other steps are equal. Okay. All other steps are equal except these numbers. In the case of root 5, you will find 5. In the case of root 2, you will find 2. In the case of root 3, you will find 3. That is the only difference. Everything else is same. Okay. So I will be proving this one only. Prove that root 5 is irrational. For root 2 and root 3, you can go through the textbook. Okay. If you can understand this, then definitely you can understand that one also. Okay. So let's discuss this. Prove that root 5 is irrational. We'll be proving that root 5 is irrational. For that, we will use a very interesting method. The method is known as contradiction method. Okay. By using contradiction method, we can prove that root 5 is irrational. Okay. So according to this method, in the beginning, we will assume the opposite of what we need to prove. Okay. For example, here we need to prove that root 5 is irrational. Okay. That is what we need to prove. So in the beginning, we will assume the opposite of that. Opposite of that means root 5 is rational. Root 5 is irrational. That is what we need to prove. Its opposite means root 5 is rational. Opposite of irrational, rational. So we will assume the opposite first. We will assume that root 5 is rational. Okay. Then we will, with that assumption, we will move forward. Okay. We'll move forward. And at the end, we will reach a mathematically contradictory statement. Or we will reach a mathematically wrong statement. Okay. From that statement, we can conclude that this mistake has happened or this contradiction happened only because of our wrong assumption, because that is the only possibility. Okay, that is the only possibility. All other steps between them, we did all steps correctly. Okay, or we are going to do all the steps correctly. So the only possibility of mistake, only possibility for the reason of this contradiction is our assumption. So we can conclude that our assumption is, or our assumption was wrong. So the opposite of our assumption is correct. Assumption of wrong means its opposite is correct. So if our assumption was root 5 is rational, its opposite is true. Root 5 is irrational. So that is the proof that root 5 is irrational. So let's start the proof. First, we will assume the opposite. Okay. First, we will assume the opposite. Opposite of root 5 is irrational means root 5 is rational. Okay. Root 5 is rational. We will start with that assumption. Okay. Yeah. So we will start with the assumption that root 5 is rational. If root 5 is rational, we can apply all the properties of rational numbers to root 5, right? And the important property of rational numbers is that it can be represented in P by Q form, where P and Q are integers and Q is not equal to 0. And without common factors also. That is also important here. I'm repeating, if root 5 is rational, or if any number is, if you have any rational number, you can represent it in P by Q form, where P and Q are integers and Q should not be 0, denominator cannot be 0. And also P and Q does not have any common factors. That is also possible. I will explain here. For example, here you have 2 by 6. Okay, 2 by 6. This 2 by 6 is a rational number because 2 is an integer, 6 is also an integer. So this 2 by 6 is a rational number. Okay, but we can simplify this 2 by 6, right? Because there is a common factor between 2 and 6. Okay, both are divisible by 2, right? So you can divide this 2 by 2 and 6 also by 2. 2 by 2 becomes 1 and 6 by 2 becomes 3. So this 2 by 6 can also be written as 1 by 3. And this 1 by 3 is the simplest form. This is the most simplified form. You cannot simplify it further because there is no common factor between them. Okay. Similarly, let's take another example. 12 by 16. 12 by 16. 12 is an integer, 16 is also an integer. One integer by another integer. So this is also a rational number. Still, we can simplify this, right? Because there is a common factor between, or there are many common factors between 12 and 16. The greatest one is 4. Okay. HCF between 12 and 16 is 4. So you can divide both 12 and 16 by 4. 12 by 4 becomes 3 and 16 by 4 becomes 4. So this 12 by 16 is also equal to 3 by 4. This can represent, we can represent this like this. But with this 3 by 4, you cannot simplify it further. This is the most simplified form, or this is the simplest form. Okay, here in this case 1 by 3 is the simplest form. In this case 3 by 4 is the simplest form. Like this, we can find the simplest form for all rational number. If you have any rational number, you will always find a simplest form. Simplest form means we cannot simplify it further. That means we cannot find a common factor between them. You can simplify that only if you have a common factor between them. Okay, so here you can always find a simplest form without a common factor between them. Okay, so you can represent any rational number like this without a common factor. So here, come back to our root 5. Root 5. This root 5, we have assumed that it's a rational number in the beginning. That means all the properties of rational numbers are applicable for this root 5. Okay, that means we can represent this root 5 in p by q form, where p and q are integers and q is not equal to 0. And the last one, we cannot find any common fact, or there is no common factors between p and q. That is the most important one here. Okay, so you can write root 5 equal to that p by q. Okay, root 5 equal to p by q. P and q are integers, q is not equal to 0, and there is no common factors between them. Okay, now with this equation, I'm going to square on both sides. Okay, if you have an equation, you can square both sides of the equation. Okay, both left side and right side. Like that, I'm squaring here. If you square root 5, that square and root will cancel, you will get 5 only. Or the square of root 5 is 5. Is equal to, on the other side, p square by q square. It becomes p square by q square, because square of p is p square and the square of q is q square. So 5 can be written as p square by q square. Okay, now in the next step, I'm taking this q square to the left side and taking this 5 to the right side. We know that if you take a number, or if you take an expression from left side to right side, if it was in the denominator, it will move to the numerator, and the numerator will move to the denominator if you're taking from left to right or right to left. So this q square will move to the numerator on the left side, and this 5 will move to the denominator of the right side. So you will get q square equal to p square by 5. Q square equal to p square by 5. What does this means? If you are dividing p square by 5, if you are dividing this p square by 5, you are getting q square. Q is an integer, so q square is also an integer. That means you are getting an integer after dividing p square by 5. That means p square is divisible by 5. Which means, according to our last theorem, p is also divisible by 5. I hope you remember our last theorem. If we have a prime number that divides a square, then that divides a also. Or if a square is divisible by p, then a is also divisible by p, where p is a prime number and a is any positive integer. Same theorem. Here, p square is divisible by 5, and 5 is a prime number. P square is divisible by 5, so p is also divisible by 5. Okay, so we can write 5 divides p square. Okay, this is the meaning of that last equation. 5 divides p square. Then, according to our last theorem, 5 divides p also. Okay, 5 divides p. Okay, 5 divides p. Now let's move on. Then, what is the meaning if 5 divides p? If 5 divides p, we can write p equal to 5c, where c is an integer, right? If p is divisible by 5, or if 5 divides p, as you can see here, that means if you divide p by 5, you will get an integer c. Let's suppose it is c. So p by 5 equal to c, that means p equal to 5c. Okay, so you can write like this. If 5 divides p, then p equal to 5c. Now square both sides of this equation. P equal to 5c. Take that equation and square both sides. So p becomes p square. P square equal to, on the other side, you can see 5. If you take the square of that 5, it becomes 25. Okay, 5 square is 25. And c becomes c square. So p square equal to 25 c square. This you will get if you square both sides of the equation. P square equal to 25. Now, let's call this equation is equation number 1. And this is equation number 2. Okay, compare these two equations. Equation 1 and equation 2. Both of these equation contains p square, right? In equation 2, you have p square. In equation 1 also you have p square. P square is common. So you can substitute this for this p square, okay? According to equation number 2, p square equal to 25c square, okay? So you can substitute this value of p square, 25c square. You can substitute this in the first equation. So that first equation becomes q square, already there on the left side, no change for that, equal to, on the other side, p square. For that p square, you can substitute this, 25c square. So 25c square divided by 5, okay? 25c square divided by 5. Now what is 25 divided by 5? It is 5. So for this 25 by 5, you can write 5. So that equation becomes q square equal to 5c square. That 25 by 5 became 5. Okay, q square equal to 5c square. Okay, if you take this 5 to the left side, that becomes q square by 5 equal to c square. Okay, q square by 5 equal to c square. Okay, what is the meaning of this? If you divide q square by 5, you are getting c square. C is an integer, so c square is also an integer. Okay, so if we are getting an integer after dividing q square by 5, which means q square is divisible by 5. If q square is divisible by 5, according to our last theorem, or the same theorem, the theorem that we have applied here, okay, according to that theorem, 5 is a prime number. So according to that theorem, if 5 is dividing q square, then 5 divides q also. Okay, so we can conclude that 5 divides q square. That means according to our last theorem, 5 divides q. Okay, 5 divides q. Here we have reached a contradiction. Which is that contradiction? According to our assumption, this assumption, root 5 equal to p by q. Root 5 equal to p by q. And p and q does not have any common factor. That is a part of our assumption. That is the property of rational numbers. Okay, that was our assumption. Root 5 is rational number. So there is no common factor between p and q. But what we have reached here, here you can see 5 divides p. And here you can see 5 divides q. So 5 divides p and 5 divides q also. That means both p and q are divisible by 5. That means for both p and q, 5 is a factor, which means 5 is a common factor between p and q. This is a contradiction to our assumption. We have assumed that there is no common factor between p and q, but here we have reached at a statement which says 5 is a common factor. So according to our assumption, there is no common factor, but here we have reached that there is a common factor 5. Both are opposite, both are contradiction. So from this contradiction, we can conclude that our assumption was wrong. This assumption was wrong. That means opposite of our assumption is correct, which means root 5 is rational. That was our assumption. It is wrong. So the correct statement is root 5 is irrational. Okay. So in this way, by the method of contradiction, we can prove that root 5 is irrational. Okay. Hope this question is clear for you. Let's move to the next one. We need to prove that 3 plus 2 root 5 is irrational. Okay. You can find the similar questions here. 5 minus root 3. Okay. So here here you can see the solution also below that. So I'm not discussing it that now. Here I am taking this one only, because here we don't have any solution in the textbook. So that's why I'm taking this one only. If this one is clear for you, you can easily understand the previous one. Okay. So let's prove this. Prove that 3 plus 2 root 5 is irrational. Okay. We need to prove that 3 plus 2 root 5 is irrational. For that also, I'm using the same method, the method of contradiction. Okay. So to prove that 3 plus 2 root 5 is irrational, we will use the method of contradiction, the same method. That means first we will assume the opposite of that. Okay. First we will assume the opposite of that. Then we will move forward with that assumption. Then we will reach a mathematically wrong situation. Now, from that contradiction or from that wrong situation, we can conclude that our assumption was wrong. Okay. So that is our method, same method as the previous question. Okay. Yeah. So our question is 3 plus 2 root 5. Okay. 3 plus 2 root 5. This is our number. Okay, we need to prove that this is irrational. For that, as I told you, we will use the contradiction method, same method. That means first we will assume the opposite of this one, opposite of what we need to prove. Here we need to prove that 3 plus 2 root 5 is irrational. So we will assume the opposite of that. 3 plus 2 root 5 is rational. If it's rational, then you can apply all the properties of rational numbers. The most important property of rational numbers is that you can represent it in P by Q form, where P and Q are integers and Q is not equal to 0. Okay, so you can write 3 plus 2 root 5 equal to P by Q. Okay, 3 plus 2 root 5 equal to P by Q. Now, let's take this P by Q to the left side and plus 2 root 5 to the right side. So that P by Q become minus and 2 root 5 also became minus. P by Q became minus in the left side and 2 root 5 became minus in the right side. So the equation becomes 3 minus P by Q equal to minus 2 root 5. Okay, 3 minus P by Q equal to minus 2 root 5. Now take this minus 2 to the left side. Here it is minus 2 multiplied by root 5. Here we are multiplying with root 5. If we take this multiplying root 2 to the other side, it becomes dividing root 2. It will move to the denominators on the left side according to the rule. Okay, so you will find 3 by minus root 2. This minus root 2 you can see in the denominator, minus P by minus 2Q. Here also you can find the same 2. Okay, these 2 minus 2's are from the right side that we have taken from the right side, equal to root 5 only. If you have taken this minus 2, then you will be left with only root 5. Okay, so this is our new equation. 3 by minus 2 minus P by minus 2Q equal to root 5. Okay, now this 3 by minus 2 can be written as minus 3 by 2. You can interchange the minus sign between numerators and denominator. Okay, and this minus and minus will get cancelled. Both becomes plus. So you will get minus 3 by 2 plus P by 2Q equal to root 5. We have reached this equation. Now there is a huge mistake in this equation. Okay, there is a huge mistake because minus 3 by 2 is a rational number. Okay, this is a rational number. Okay, minus 3 is an integer, 2 is also integer. Similarly, P by 2Q is also rational number. Okay, that is also rational because P is an integer, Q is also an integer, so 2Q is also integer, so P by 2Q is rational. And these two numbers are rational. If you combine two rational number, you will always get a rational number only. Okay, if you add any two rational number, you will only get a rational number. That means this complete left side is rational. But what about root 5? It is irrational. We have proved the same thing in the last question. Okay, this is irrational. Okay, this is a contradiction because a rational number and an irrational number, they cannot be equal. Okay, rational numbers are always different from irrational. It's not possible for an equality between them. Okay, so this is a mathematically wrong statement. So we can conclude that we did this mistake because of our wrong assumption. So for our assumption was wrong. This was wrong. Okay, so 3 plus 2 root 5 is not a rational number. It is an irrational number. Okay, in the same way, we can prove this also. Okay, here I am not taking 6 plus root 2. This is same as second question, so I'm not taking this. And these two are similar questions, so I'm taking only one of them. Okay, I'm taking only 1 by root 2. You can apply the same method to second question. Okay, so 1 by root 2. Now let's prove that 1 by root 2 is irrational. For that also, we don't have any different method, only the same method, the method of contradiction. Okay, by the method of contradiction, we can simply prove that 1 by root 2 is also irrational. Okay, so let's prove that. For that, in the beginning, as we did with this question, we have to assume the opposite. Okay, we have to assume the opposite. That means 1 by root 2 is rational. That is the opposite of 1 by root 2 is irrational. So if 1 by root 2 is rational, it can be represented in P by Q form. Okay, now take this P by Q to the left side and 1 by root 2 to the right side. So what will happen? P by Q becomes Q by P. This will happen if you take a rational number to the from one side of equation to the other side. It becomes the reciprocal. Similarly, 1 by root 2 becomes root 2 by 1. Numerator becomes denominator and denominator becomes numerator. This will happen if you take anything from right to left or left to right. So this p by q becomes q by p equal to 1 by root 2 becomes root 2 by 1. Okay, that means q by p equal to root 2 by 1, 1 means root 2 only. This is actually a wrong statement because q is an integer, p is also an integer. So q by p is rational number. Okay, this is rational. But what about root 2? Root 2 is irrational. Okay, you can prove it. You can prove it by the same method of root 5. Okay, we have explained the method of proving the irrationality of root 5. You can use the same method for root 2 also. So this is irrational, root 2 is irrational, and this one is rational. So this is not possible. Okay, a rational number cannot be equal to irrational number. So we have reached a mathematically contradictory statement, a mathematically wrong statement. From that wrong statement, we can assume that, we can conclude that our assumption was wrong. This mistake has happened only because of our wrong assumption in the beginning, which says 1 by root 2 is rational. That is wrong. 1 by root 2 is actually irrational. That is the correct assumption. Okay. So students, I hope all these topics and all these questions are clear for you. In the next video, we'll be discussing about polynomials. Okay, we have covered almost all the important topics of real numbers. Okay, so from the next video onwards, we will discuss about polynomials. Okay, so I hope all of you have enjoyed this video. Okay, so thanks for watching. See you in the next video. Take care. Bye bye.